Just briefly, our consortium, and I think this is one of the best things about the R user community. We are open, considerate, and respectful. So we do abide by the R consortium code of conduct. So please keep that in mind through all your interactions with CalgaryR. We've got a ton of people behind the scenes that help make sure that our events are a success. So thank you to Shell, Cliff, Adamus, John, Byron, Dylan, and Jennifer for keeping us going through these times. Briefly, we love speakers. We love a diversity of topics, no matter how deep. Today is one of the first times we've had something on solar, so I'm personally super stoked about it. But don't worry about imposter syndrome. CalgaryR is a wonderful place to share knowledge and learn. So we're looking for a ton of topics. If you feel like you have something to volunteer, please reach out to us afterwards. We'll be more than happy to try to find a good topic that would meet the audience. So that's great. So thank you. Okay, so without much further ado, I am introducing Abed. Abed is presenting today on exploring Alberta's solar resource through R. He has 7 years of experience with R, from mostly GIS and cartography. More impressively, he's lived in 10 cities, and he's currently living in Edmonton, which is where I actually grew up. So welcome to Alberta and welcome to Edmonton. For those of you who have just trickled in late, we are going to take questions in through Slido, through the CalgaryR room. So if you have any questions, we'll queue them up there. That's going to be the most effective place to submit your questions. So with that, I am going to stop sharing my screen. And Abed, I will ask you to share yours and we will get rolling. So thank you. And in the spirit of buying Abed an extra minute, the link to Slido is now in the chat. Feel free to log in there and do that. Abed, take it away. Thank you very much.
Can you guys see this? Can I just get like an oral confirmation from John or someone that you can see the first slide?
You have an oral confirmation.
Okay, brilliant. Okay, so I would just want to say thanks to the CalgaryR members for having me. I hope nobody minds that I mentioned by name Jonathan Lin, Chell Healy, and Cliff Subchuk. I know there's a lot of other work that went in the background, but those were the 3 people whose time I took up a lot of. And of course, thanks to all of you individually. I can see about 30 people, I guess, on this Zoom meeting for taking some time out. And I will tell you a little bit about R and a little bit about how I use R for solar energy. So the wonderful thing about R as a language, as a technology, is that it has so many different groups of people using it. And I've kind of pitched this talk at like the Venn diagram of people who could benefit from this talk might be R users who are a little bit curious about solar energy and what it is, people who are already in the solar energy or renewables field, and might be looking for an alternative to tools they already use. So for example, PBlib is a pretty good Python library, very extensive, but has a horrendous learning curve.
Hey, Abed.
Hello?
Sorry, John here. Do you mind speaking just a smidge louder? I think I'm just getting some feedback on probably I've just cranked up my audio so loud I never noticed, but if you don't mind speaking a bit louder, that would be great.
Okay, I'm gonna do my best to do that.
Without waking up your daughter, of course. Thank you everyone for their feedback.
I am, let me just, audio settings, I'm gonna try this. Yeah, no, I think this is, I can try speaking this loud. Does that help?
Someone in the chat, tell me if this loud is good enough. A little bit. Okay, so
Okay.
we'll run with that.
All right, I will do my best. If it becomes too much of an issue, I can try to think of another way. But for now, I'll speak in my loud voice. So what I was going to say is that my target audience is pretty diverse, just like the R user community. And you might just, be a person on a lark. You might just have very little to do at 6 p.m. In Alberta on a Wednesday afternoon. But what I do ask is that to make the most out of this talk, you should have some idea of numeracy and scientific literacy, just at the level of like what I would think of as high school physics. And to get the most out of the coding examples towards the end, you would probably need to know a little bit about computer coding. And what I'm going to hope to achieve is I want to tell you guys a little bit about the worldwide solar resource and its relationship to geography, explain the photovoltaic effect, explain why I think data analysis and tools like R, which have been designed kind of to do data analysis and statistics, are good, are valuable. And I'm going to do a practice run with some data from Alberta. And I want to talk about R and solar data in general and have some fun. I should say I will do my best not to tell any lies in this talk. However, it's impossible that I would be able to completely tell the whole story in the most strictly true sense possible. But nothing I say here is going to be a lie to the best of my knowledge. So the sun and us. I did once, a couple of years ago, meet a flat earther who lived in Vancouver. It was a strange experience. The sun is a sphere just like the Earth. The Earth is roughly tilted at 23 degrees on its axis and revolves around the sun. An interesting outtake from this is that the Ptolemaic model, which is the model of the sun revolving around the Earth, is actually still used in a lot of solar energy applications. We won't actually be doing that today because we're not going to be talking about things like solar azimuth and so on, and solar elevation angles, where it sometimes makes sense to adopt the fiction that the sun revolves around us instead of the other way around. But the point is that the sun is basically a runaway hydrogen bomb, and it's about 150 million kilometers away. By the time the sun's radiative energy hits us, we are bombarded with something like 1.7 times 10 to the 17 joules of energy per second, or 1.7 times 10 to the 17 watts. And it works out, if you look at the radius of the Earth, as about 340 watts per meter squared. But what does that actually mean? If you remember Back to the Future, the DeLorean, according to Doc Brown, required 1.24 gigawatts. That was the one point of the film that really kind of sticks with me, is that 1.24 gigawatts is kind of like meaningless, because how long is the 1.24 gigawatts actually running for? If you're running it for, a couple of seconds, that's actually a lot of energy, but you might be running it for, a femtosecond, and then it doesn't really matter. So, but let's just run with it and say that the sun's energy reaching the Earth could power a journey from 1985 to 1955 about 1.4 million times in a DeLorean. A quick review. So a joule of energy is basically increasing the acceleration, giving 1 kilogram of mass an acceleration so that it increases by 1 meter per second. A watt is just 1 joule of energy, or 1 joule of work done in 1 second, or 1 joules times the Hertz, right? If you want to go down to like kind of a smaller level, and you want to think about the basic electric charge, which is the charge on an electron or a proton, it's like 1.6022 times 10 to the 19 coulombs. So we can go from the SI system to something like saying that 1 watt increases the potential energy of 6.24 times 10 to the 18 electrons by 1 volt. And that's going to be, you're obviously not going to be expected to remember that, but it helps to frame the discussion that we're going to have about the photoelectric effect, which is the kind of core of the PV cells that power solar energy. I should have perhaps said by now that I'm going to concentrate this talk exclusively on photovoltaic or PV electricity, and ideally things that you get out of the grid. I'm really a believer in the kind of grid-connected PV, and we can talk about that in a question and answer session towards the end. To bring things to a kind of a more human perspective, instead of thinking like a watt is doing 1 joule of work in 1 second, you could think of a kilowatt hour, and a kilowatt hour is doing power work at the rate of 1 watt, at the rate of 1,000 watts continuously for 3,600 seconds, i.e. 1 hour, right? And if you regularly charge your phone every night, a smartphone, it's between 2 and 6 kilowatt hours in a year that you're using. That means like fully discharging your Android's battery and then charging it at night before you go to bed. I think the Android is closer to 2 than 6. And if I'm not mistaken, the iPhone is closer to 6 than 2. It's also, worthwhile looking at your electric bill from time to time. So we've said that, and after that segue about energy and power, I want to go back to what solar radiation actually means in terms of where it falls on the Earth and how much do we get it. In this table here, I've got a series of 10 cities, longitude and latitude, and the annual GHI. GHI stands for Global Horizontal Irradiance. I will get to that in just a couple of slides. The important thing to understand is that this is kind of like the major type of solar radiation that you can expect, right? So you can see that cities like Calgary and Edmonton, when you compare them to cities at the same latitude or similar latitudes, they actually do quite well. So Berlin, which is and Utrecht in the Netherlands, which are kind of just between Calgary and Edmonton in terms of latitude, both get significantly less solar radiation than cities in Alberta and indeed cities in the Canadian prairies. And I just wanted to sort of map this out, and you can see that indeed, as one would expect, a city like Doha, Qatar, which is just on the edge of the Persian Gulf, gets quite a lot of solar radiation, right? But that, their latitude is like 25 or something. But indeed, Canadian cities in the prairies do well when you compare them to European cities. Now, I said so far what I was talking about was GHI. So to explain this 3-letter acronym, if the sun were indeed a point source, we could expect that if you had a flat PV panel made up of PV cells, photovoltaic cells, that you would get solar radiation which was falling straight down. In reality, however, and this is called DNR, or direct normal radiation. In reality, however, what you expect is that some of it will come down from the clouds. Or diffuse radiation reflected from the atmosphere. And that would be called diffuse. So GHI takes account diffuse radiation bouncing off, for example, clouds. And now I want to go from global horizontal irradiance to plane of array, or POA. And this is really important for Edmonton in a quantitative way. And I have to apologize because since I began talking to Jonathan and the others about this talk, I've constantly been kind of rolling back my ambitions. I won't be able to talk about the plane of array irradiance in a kind of a quantitative way. But what I can tell you is that a very important thing in the Albertan context is this thing that we call albedo. Albedo is a fancy way of saying reflection off the surface of the Earth. And when you have a tilted solar panel, and if you can kind of just imagine this very simple ray diagram that I drew in like LibreOffice or something, you do indeed have this direct normal radiation. You have this diffuse radiation that comes in, from the clouds or water droplets in the atmosphere. But then you also have a component of solar radiation which is reflected off the ground and hits the panels, and that is directly proportional to how reflected the ground is. And, well, albedo is particularly high in a place like Edmonton, and it's significant, and it's especially high during the winter months. And the simple reason is that snow that sits on the floor, on the ground, rather, is very reflective. As a kind of another segue to this talk, I'm not going to talk about climate change. Obviously, I am a believer in climate change, but we're not going to talk about it today. And it's an important reason for why we should think about solar energy. But one thing that you should be aware of is that the polar ice caps are a major source of albedo for the Earth as a system. So one of the things that's particularly worrying over the next few years is, are the polar ice caps actually melting faster than the Earth can handle? If they are, the Earth will not be able to reflect back solar radiation, and that becomes what you would call a positive feedback loop on global warming. Now, that's a whole other story. If we focus on 3 cities that I've just taken from random, Buenos Aires I have yet to visit, but I do hear very good things about Argentina, so I hope to go there one day. And the albedo there is high, but it kind of remains stable. Edmonton is like a clear winner compared to a city like Utrecht, which is at a very similar latitude, but does not get a lot of snow. Meanwhile, a city like Utrecht, shown in both charts in red, does have a lot of cloud cover throughout the year. And what that means is that the diffuse irradiation hitting a flat or tilted solar panel in a city like Utrecht or at that latitude is going to be relatively high. Again, going back to our 10 random cities selected across the world, you can see that, for example, a city like Ramallah on the Palestinian West Bank does not get a lot of diffuse radiation because there isn't really a lot of cloud cover there. Whereas, for example, Utrecht over here actually gets quite a bit, and Berlin gets even more. If you've ever been to Berlin, it's a very, very cloudy city. And that kind of, in a very qualitative, in a very simple way, that is the first part of my talk, right? We get a lot of solar radiation from the sun, right? You can run the DeLorean 1,000,000 times plus, right? From the solar energy we get. In fact, one statistic which I really wanted to mention is that one very clever person has come up with this calculation that the amount of solar radiation that hits the Earth in 1 hour is enough to account for all of our energy use for the course of a year. In the next part of the talk, we're going to understand why that's not exactly true, right? And it falls unequally on different parts of the globe. This is not just to do with latitude or the time of day. Indeed, solar energy is intermittent. When the sun goes down over the horizon, we can't use solar panels anymore. But it's also to do with other kind of geographical and meteorological effects, such as the jet stream, which carries kind of warm air from the Caribbean into Europe, makes it warmer in a place like the Netherlands, where I was living before moving to Alberta, than it is in Alberta. But it also brings a lot of cloud cover, and that has an impact on how much solar radiation hits solar panels in those countries. And I also hope that we're taking away here that the different components of solar radiation are an important thing. So for example, if you have tilted solar panels, the angle at which you tilt them depends on where you are in the globe. Again, unfortunately, we don't have time to cover that today, but I think it's important for people to know that direct normal radiation and diffuse radiation and also ground reflected radiation related to albedo are significant things, especially when we're talking in the Albertan context. Now I just want to jump to the kind of the photovoltaic effect. The photovoltaic effect is actually one of the three things that Einstein did in his miraculous year in 1905. He helped kind of uncover it. But and it was actually something that people had noticed since the late 19th century, maybe even mid 19th century. I'm not 100% sure. But basically, what it means is that uh, in a semiconductor, you will have electrons living in a valence band. The photons come from solar energy. They have an energy E, which is directly proportional to their frequency. This is the Greek letter nu, not V for frequency. And thus inversely proportional to the wavelength of the photons. This is the Planck constant for those of you who don't know. So when there is the right, correct type of photon hitting a semiconductor in a PV cell, right, it pushes an electron into the conduction band. If you are a solid state physicist or an electrical engineer, you might be hyperventilating right now because you might have seen how I completely butchered and simplified this explanation. I want to assure you that I butchered and simplified it simply because I wanted to make it as accessible to a wide range of the audience as possible. I'm not going to talk about things like the Fermi levels that exist in a semiconductor, and I'm not going to talk about the creation of electron-hole pairs. The important thing for the average R user, I would say, to understand is that we can push electrons into the part of the semiconductor where they can then conduct electricity. And we can also, it is important to mention, I guess, that the creation of the right voltage differences is important so that the current moves only in one direction. I said semiconductors. This is an important part of the talk that's going to come back and bite us later. I'm focusing on crystalline silicon semiconductors, right? Because as of today, and I actually checked this up as recently as today, 95% of the global connected PV panels, especially the grid connected ones, are made up by crystalline silicon, right? There are good reasons why people don't talk about these thin film technologies, although they are super cool and they do use conducting materials. They're just not cost effective right now. Cadmium telluride or CDTE panels like cells are actually doing really well in terms of efficiency improvements, but the cost of generating them is just not the same as silicon panels. Thanks in large part to China, which has done the heavy lifting for the world's industry in terms of producing PV panels. They now don't cost that much per kilowatt hour. Per kilowatt peak. And some constraints on the photovoltaic effect. So the first kind of big constraint on the photovoltaic effect, and here again, we're talking about crystalline silicon panels, or crystalline silicon cells. There's obviously a technical difference between talking about cells and talking about panels. We'll get to that in the Q&A, I suppose. One of the big constraints, or the first ones, might be the transmittivity of the covers, right? So that's always imperfect. It's pretty good right now, but it took a while to get here. And right now, sort of 90% of the radiation that hits a solar panel will actually get to the cells. The other one, and this is what is technically called the Shockley-Quasar limit. I've left out the technical term Shockley-Quasar limit because if you Google it, you find that a lot of people are finding ways around it by using multi-junction cells. That's kind of outside of the scope of this talk for today. But basically what it means is that in the solar radiation is made up of a profile like this, right? And so this is meant to show you the kind of the flux or the irradiance. And this is the, you can think of this as a proxy for the number of photons hitting a square meter of Earth anywhere. And this is and the wavelength over here is, of course, inversely proportional to the energy of photons. Now, at some point here, all of these photons might not have enough enough energy for 1.3 electron volts. And that means that that 1.3 electron volts is what you need to push an electron up from the valence to the conduction band in a crystalline silicon PV cell. Likewise, photons with energy that is greater than the band gap, and I should have perhaps used the word band gap here. That's just a fancy way of talking about the gap between the valence and conduction bands, or the potential energy difference between them. Photons which have an energy that is greater than the band gap energy, that is also like excess energy, and that's lost. One of the things that's really important in the PV effect in general is that that energy that's lost adds to the thermal energy in the PV cell as a whole, and the increased temperatures in the PV cell as a whole drive down the efficiency. And the reason they drive down the efficiency is, well, the fancy word is it helps to accelerate the what's called the recombination effect. And that means that basically, well, for the purposes of this talk, it means that some electrons are going to go the other way and recombine with a whole without contributing to the overall transfer of electrical currents in the PV cell. Now, efficiency and yield. At this point, we are going to be able to quantify a little bit, in a manner of speaking, the efficiency and the yield from PV cells or PV panels. Now, on a global level, and these figures are from 2018, on a global level, there's 504 gigawatts of installed grid-connected PV panels. That's 417 DeLoreans, if you're counting. And they generate 585 terawatt hours of electricity, and that equates to a capacity factor of 13.25%. If you're from the power industry, a capacity factor is a way of saying the amount of energy, electrical energy generated, fed to the grid by a generator compared to the peak power of the generator, right? So if you have if you own a 1 megawatt PV farm and you're feeding it into the grid, you can run it for 8,760 hours. And so you can, in theory, produce like 8.76 gigawatt hours of electricity. Now, for obvious reasons, PV panels do not perform as well in terms of capacity factor as, say, a coal-powered fire plant, right? But 13.25% is actually quite low. Some of the better and more recent PV panels or PV farms, let's call them, are hitting 20 and above percent as a capacity factor. And the reason is that the efficiency of the panels has been improving. And they've been installed in sunnier places. Many of the, like about 10 or 12 years ago, many of the earliest big PV sites were being done in places like Germany. And it's really wonderful that the Germans kind of subsidized the PV industry to the extent they did. But the fact is that Germany does, as a whole, just does not get a lot of sun. And so this kind of brought down the capacity factor. So the capacity factor, I've had a lot of interesting discussions with people on the internet who've been trying to tell me that, you know, solar energy doesn't work, but it actually does. It's just that there's a kind of a learning process. It's called technological learning in terms of improving the efficiency, and the panels are constantly getting better. The cell technology is getting better. And where we're deploying them is getting better too. But leaving the kind of the global picture, going down to Alberta, I want to talk about the conversion efficiency of the panel, right? And the conversion efficiency of the panel, which I'm going to here give the Greek letter nu, is basically, It's the proportion of the yield, which is the amount of PV energy that I get from my panel, over divided by the insolation. That's the amount, that was the figures that we were looking at earlier, right? And interestingly, you can model mu by looking at the standard test conditions efficiency, and then it decreases with the operating cell temperature, but increases as log base 10 of the irradiance I. Beta sub R, beta sub ref in the literature, and gamma are material specific values. There's a surprising amount of discussion in the academic literature about what these values should be, but in general, you know, they kind of land, like I'm always surprised at how frequently papers are published on this. So it's not set in stone, but we have a general idea of what these values should be. And we'll talk about that when we go through the coding example. So we said this operating cell temperature, and then I've given it this, this prime notation here. And that's because I've taken the cell temperature and I've subtracted 25 degrees Celsius. Now, what is the operating cell temperature? The operating cell temperature is in fact the ambient temperature. That's the temperature, that's the one that you're kind of, you know, used to from the weather report. That's the temperature of air at an elevation of 2 meters away from the sun, and at assuming a wind speed of 1 meter a second, right? So there are, and this one is actually kind of, you know, you can get like, maybe not controversies, but you can get some discussions about it. But a cell temperature is the ambient temperature plus a function of the irradiance. And the irradiance here is the insolation or the solar energy divided by time. And these, again, material specific values of U0 and U1, and then the wind speed in meters per second. There is a good story that I'm going to tell you in a couple of slides about the importance of units. So keep the units in mind, but that everything here, unless I say otherwise, I'm always talking in SI units. Anyway, here we go. Sorry, my wife noticed this slide, and she noticed that it's actually, the site that I'm talking about is actually called OkCupid and not Hello Cupid. So my apologies. So why am I talking about OkCupid? If you've noticed, if you keep your eye on the news, there's no shortage of people looking for ways to slap a sticker called data science or statistics or machine learning on a lot of things that may not necessarily merit that kind of discussion. And I think a lot of this is trying to build off of OkCupid. So OkCupid was really successful at predicting, you know, who your significant other should be based on things like, you know, how you take your coffee. And it's amazing. It's an amazingly successful website. If you meet your significant other through OkCupid, you're more likely to become married, and you're more likely to stay married, all right? But why would we, everything I've said so far is a kind of a watered down, very watered down physics discussion or a question of meteorology. So why should I use R for this? Well, you should use R because R is really good at crunching numbers. And we can simplify a very complex meteorology and physics discussion to a number crunching exercise. Now, in some data sets, for example, that I may have worked with in our last summer, as recently as last summer, I was looking at some data sets that had 30-second resolved insolation data and irradiance data, wind speeds, and so on from a particular site that was in Europe. And if you divide the 8,760 hours in a year into 30-second intervals, what you get is about a million readings, right? So that's like a million rows of data. And if you assume that the sun is only shining for about half of the year, half of the hours in a year, that's about 500,000 rows. But you also have, significantly, you have columns that are, you know, you need to watch out for insolation, you need to watch out for wind speed, and you need to watch out for ambient temperatures, because all of those play a role in determining cell temperature. The cell temperature plays a role in determining the efficiency, and the efficiency, of course, is directly related to the yield. And the yield is what you feed into the grid. Like in the end, this feeds into the decision variable that you have, which is the LCOE. The E in LCOE can be either energy or electricity. It's the levelized cost of energy or electricity. If you look at your electric bill, it'll give you something like it. It'll tell you like how much money in dollars you've spent per kilowatt hour, right? And this is where the land comes in for solar farms, PV farms, particularly in a place like Alberta. So the LCOE for any kind of electric utility that generates electricity and feeds it to the grid is going to be the costs. And the costs for an electric generator are going to be operations and management or operations and maintenance, fuels, which obviously in our case is going to be zero because the sunshine is still for free, at least for now. The investment costs, now these are generally expressed in terms of dollars per kilowatt peak of the panels. I believe in Europe, they now talk about 1,000 euros per kilowatt peak to install a PV panel. One of the things that happens in solar energy that is not the case for conventional or thermal generators is the cost of land. And this is particularly true for the plane of array kind of situation that I was talking about earlier with the tilted panels. So tilted panels, you need to assume that at least I would say about 1/3 of the land that you need is empty. So you can only utilize about 2/3 of the land, right, to put solar panels on, because you need to keep space between the rows of the panels. Otherwise, if you have tilted panels, they will shade one over the other. Inter-row spacing, outside of the remit of this talk for now, but it's when I do give you guys the slides, I will add a few more slides that explain the importance of this. And finally, you'll notice here that it says NPV at the top. NPV is a fancy way of saying taking time into account. We're basically taking inflation into account. I honestly sometimes struggle with thinking about the NPV of electricity. Money is just a human fiction, but electricity is kind of a physical reality. But it kind of makes sense because you do take the NPV of the money, so you should take the NPV of the electricity as well. And you will come up with, by saying like, you look at the yields, and you can obviously see that sites with a higher PV yield will have a lower LCOE than sites with a lower yield. So what are the prizes you take home for part 2 of this talk? Cell operating temperature inversely corresponds to the efficiency of PV yield. And cell operating temperature is directly related to the ambient temperature and is also a function of the cell technology. You can simplify also this like physics and meteorology issue to a question of number crunching exercise, which is what R is really good for. And knowing how much yield you get from panels allows you to calculate how economically feasible it is for you to install solar panels, let's say on your home. So we can do this at home, right? I've called this the Kohl table, Kohl spelled K-O-E-H-L, and I've just like hardwired it into my R environment. I will be sending, like I said, a fuller set of slides to the CalgaryR users group. And also I'm very happy to share whatever codes I can share with you guys from my blog or within this presentation. This is taken from a paper called Swing Shackle and co-authors from 2018. Swing Shackle is a really good paper by a guy with one of the coolest names I've ever come across in my life. And he's actually kind of like a big expert on PV technologies. And what it is, so this is the nominal operating cell temperature. This is what you expect the PV cells to operate at. You can see that all these technologies, this is like monocrystalline monocrystalline silicon. This is polycrystalline silicon, amorphous silicon, which we said would just drop out anyway. And these are thin film technologies, which again, we won't worry about. I have to say, I had a chat with Jonathan Lynn at 4 p.m. and then after that ended at 4 p.m. Then after I put that down, I realized that there was a mistake in this table, that this should actually be 15.4%, not 18.4%. And sorry, these are expressed in percentages. And that actually took up a big part of what I've been doing for the last 2 hours, is fixing the codes. But we'll get to that later. And these are the wonderful U0 and U1 parameters that we were talking about earlier. Before we jump in, it's important if you're going to follow along, and for the extended, you can ignore this for now until you get the extended slides, because we won't have time to cover everything I wanted to do today. But I wanted to mention, I wanted to give a shout out. There's a growing number of packages in the R environment through CRAN and that you can install via GitHub that allow you access to a lot of solar energy databases. One of my favorite is called NASA Power. NASA Power basically links to the API set up by the NASA Prediction of Worldwide Energy Resources, which is based out of Langley, Virginia. And they have an API that allows you to get satellite images, satellite image-based data on wind speeds, ambient temperatures, solar radiation. Adam Sparks created the wrapper called NASA Power, all lowercase and CRAN. The first thing you should do once this talk is over is install this package in your R environment and just play around with it, because it is really an awesome package. And it's about to get more awesome, and I'll talk about that later. So I'm old enough to know that you should really write all of your code in functions to make it more modular so that you can reuse it later. The Cole module, the Cole model, this is what I've called this function, which takes as parameters the ambient temperatures in a data frame, the irradiances in a data frame, wind speeds, and the specified technology. This should be in quotes when we actually use it. We'll get to that in a second. And what it does is it looks at the specified technology, selects the correct value of the U0 and the U1 parameters. Excuse me. And then it will create first of all, an empty matrix, which we will then populate with cell temperatures. And the cell temperatures, this is just an implementation of the fancy equation which you saw earlier. I actually really wanted to write more in functions, but like I said, I made a huge mistake in the codes, and I realized that when I got some kind of crazy answers that I was about to put on a slide here, and I figured that out about 2 hours ago, and it was chaos in this house. So instead, what I've done is, again, I've just created a data frame. Of course, strings as factors, and I do have to beg your forgiveness for this as well. Like it's not all fitting on the slide, but when I will fix that, this slide in particular, when I send the full slide deck over to the CalgaryR users group. And one thing I should have pointed out perhaps here is that I basically went through, I'm using monthly values from NASA Power. And that's why I have 12 columns, and I have a number of rows, which is based on the number of sites in my data frame that I'm going through. And so I've created this data frame just for you guys. Eta is, of course, the Greek eta for efficiency, and the eta of the cell's data frame. And the number of rows that I have is the number of rows, the number of places in Alberta. There are like 19 census divisions in Alberta. I did not know that before living here. I know that now. And what we do is we calculate an average cell temperature for each month in each of these 19 divisions. And then that cell temperature becomes itself a parameter for this function, which is the function that produces efficiencies. word of the wise also about units. So yeah, like I said, one of the big mistakes I made in the earlier version of this talk was that I did not take into account that when NASA Power returns data, it returns data in units of kilowatt hours per meter squared per day. And you really have to kind of take that into account, of course. And I did know this, but I somehow forgot when I made the original version of this talk. Another thing I like to do when I've worked with kind of solar data before is that I generally find a way to increase the ambient temperatures. That's because PV cells are only operating obviously when the sun shines, and in general, temperatures drop as the sun goes down. So in the example that I'm going to show you some results from in a couple of slides, what I did was I just said, well, let's assume that the ambient temperatures are increased by 40%. Funnily enough, you have to be really alert when you do this for Alberta, because in all of the sites in Alberta, there are several months where the average ambient temperature is below zero, and you just have to make sure that you don't just multiply. But I'm sure you could have figured that out by now. Irradiances are simply assumed to be the insolation over the amount of daylight hours per month. Okay, so we've talked about writing R codes that calculate PV yields from solar insolation. But where do we go? This is the glorious province of Alberta, or Wild Rose country. But you guys have all seen this map before. Everything here is made in R, but beyond the point, you don't want to map. What you want is data. So, and I'm not sure what I did was I gave each of these census divisions the name of the largest city or conurbation within them. And you can see that the global horizontal irradiance actually does vary quite a bit. Like Medicine Hat is doing really well. But another thing is that this is the plane of array enhancement, or the improvement on solar radiation as obtained by using an optimal tilt on the panels. And you can see that this too varies quite a bit. And that has to do with the fact that Alberta is quite extensive with different sites, in the far north and in the south of the province. When you have a place like Medicine Hat that's kind of in the southern part of Alberta, there's less room to go up because it's already getting a lot of solar radiation. But also when you have, it's getting a lot of GHI to begin with, but also in the kind of the snowier areas, you get more albedo. So at least this is my explanation for it. Perhaps someone here will have a better explanation for why the enhancement due to tilting varies so much within Alberta. Right, so Alberta coordinates, that would be, where was that data frame? That would be this data frame here, which has longitude and latitude as well, or we can use that. And what we do is we do a request to the NASA Power package, the NASA Power API. We use the get power function. Community SSE just means return the units that are most useful to the solar or in fact the renewable energy community. The PARS is the request, is here the temperature at 2 meters. This is just an example that I wanted to talk about. And the temporal average is climatology. Climatology means return the values for the 30-year period between 1985 and 2014. So January 1st, 1985 to December 31st, 2014 is what they return. Now, when you run this request using the NASA Power package, which I really hope you do, what you get is a tibble. And because I've worked with this package before, I know that the first 3 columns of the data frame equivalent of the tibble are completely useless. So what you want is you want columns 4 through 16. That works out as 13 columns, and the 13th column is the annual average in cases where you can get an annual average. So this is just an explanation of what we want. I can see I have about 5 minutes that I wanted to go through, but that's fine. Just keep in mind that when you try to download data from NASA Power for global horizontal irradiance, what you need to, the parameter that you want is all-sky underscore SFC underscore SW underscore down. I have a hard time kind of parsing through this one, but I think this means like downward facing solar radiation for south facing panels. And that applies to south facing panels in the northern latitudes. But you can use it, you can use it for a site in Australia and it still works. Right. Oh, yeah, important point. So as of now, you can get daily requests, so daily time resolutions from NASA Power, or the climatology one returns monthly values for that 30-year average, the climatology temporal average, right? But the beta version of the NASA Power API right now allows you hourly requests. I've put an example on my blog of how to use that their API directly to get a JSON and then convert the JSON to something that's more R friendly so that you can get our resolved data. I would not yet use NASA Power for if you're about to plan a project with a power company and then try to like kind of sell that project and get a loan from a bank. Right. However, if you're in an earlier stage of planning, NASA Power is really good and perfectly valid. And indeed, you can find academic literature where people use monthly values. So it's still fine. But if you wanted to look for like hourly resolved data, I will send a link to my blog where you can see how to use the NASA Power beta version. By July, it should be fully rolled out, and then all users should have access to it through Adam Sparks' NASA Power package in CRAN. In case you're wondering, this is what the Tibble looks like. And the question is, how did we do? Right? And I think, yeah, this is more or less the end of my talk. PV cell efficiency in Wainwright, Alberta. And I just literally, and again, the longitude and latitude that I took for Wainwright is not exactly Wainwright. And I'll talk about that in the Q&A if you want. But you can see that in general, this is a very typical site for Alberta. And in general, the PV cell efficiency is like 20% and above using an STC efficiency of 15.4%, which is not the most optimistic in terms of what the state of the art is today. And that, I think, is a really important take-home message for everyone who's here today, who's been kind enough to show up, which is that kind of using these, using R to run through this kind of high-level discussion of how solar energy can be used in a place like Alberta. There is very good evidence that PV panels operate very, very well here. And a very interesting point is that the PV panels do have their best efficiency around sort of March and April when the temperatures are not so high. And this, I think, is like a kind of it was one of the really funny discussions that I would have with people when I first landed in Canada. And I would say, yeah, I've immigrated to Canada and I'm moving to Alberta and I'm here to talk about solar energy. And they would look at me like I was crazy. It's like, well, because I'd spent a big part of my life living in oil producing countries. And now I'm coming to another oil producing part of the world. And I'm talking about solar energy. And I would say, well, no, Alberta is really great for PV panels because it has low temperature, it has high albedo, and it has reasonable levels of solar insolation all the time. So some final considerations, because I had to cut this talk short to fit everything in an hour. I've thrown about cells and panels kind of liberally, but the calculations that I've done, so this chart here, I believe, does take into account that 10% of the PV energy is does not take into account that 10% of PV energy is lost, or the yields are lost in the panel itself, right? So you have to kind of keep that in mind when you plan solar projects. The installation cost of a kilowatt peak of PV panels has dropped like I think like 97% or something in the last 20 years or so. Solar that contributes to an LCOE of solar energy, which is now significantly lower than it used to be. Grid connected PV electricity is today very competitive with thermal generators, or that's, you know, in layman's terms, that's basically like natural gas or in some cases even coal, which is an incredibly cheap form of electricity historically. 2 days ago, I think I saw a news story about Saudi Arabia installing a massive PV farm that was where the LCOE was going to be like $1 per kilowatt hour, which is insane, right? Because people used to get excited about 4 and 5 US cents per kilowatt hour for PV. But I don't think Alberta is going to compete with Saudi Arabia in terms of PV electricity a cost per kilowatt hour. However, I do think Alberta can do a lot better now. Keep in mind, though, that to really make the most of the energy, you would have to tilt the panels, particularly in a place like Alberta, so you could harvest the albedo solar irradiation. But then that has that interplay with the LCOE because you need more space. Elephants in the room. While I've been talking, I wanted to discuss the inconsistency of using, or like, let's say the flaw of using monthly data. The monthly data, like I said, you can find in the academic literature the people who use, authors who use monthly solar radiation data. It's just probably, if you're like but if you're going to be using it for a grid connected PV farm, it's something to keep in mind. I obviously, if you're, again, I'm very interested in taking this discussion further. If people want to work together, collaborate together on perhaps another CRAN package that addresses specifically the needs of the PV electricity community, you know, we can do that in the Q&A session. And the other thing, perhaps funnily enough, the largest elephant in the room is that the rate of acceleration of technological learning for PV panels is so fast that anything that I say today in a couple of years might be less than true. The biggest thing to watch, I think, in terms of trends is going to be electricity storage. So electricity storage might, if it gets to the point where the total LCOE of electricity, even counting storage, becomes competitive, then we will even get rid of the whole question of intermittency of solar electricity, and people who poo-poo on PV electricity all the time by saying things like, oh, you know, the sun sets every day, so we won't be able to turn on our lights if we switch to entirely to solar energy. I do think probably even in 20 years, unfortunately, we're going to still need fossil fuels, but PV will play a huge role in the electric grid. Right now, it's only about, like, I think 3%, but that's still huge considering how fast it's been growing the past 20 years. And like I say, I owe you all my apologies for not having found the mistake sooner. That would have given me more time to finalize the last few slides that I wanted to do. And but I will send those together with maybe more code snippets to the CalgaryR users group. Anybody else have anything to say? I think we can switch to Q&A at this stage.
Well, all right. I've just stopped sharing your screen. Abed, it's kind of funny, you fit in to Canada quite well with your apologeticness. Your presentation was fantastic, so thank you very much. Well, I'm just going to load up the questions if I can find the right browser window. But while I'm doing that, I actually thought it was really interesting during your talk where you had mentioned um, that solar energy not only comes from the sky, but also reflection off the ground. I think that's one thing I have never appreciated. So thank you very much for doing that explanation, plus the NASA power package. That's very, very cool. Um, I think everyone now can see what's on screen. The questions seem pretty kosher, so we'll just kind of go from the top down. I'll kind of acknowledge them as we go. Abed, I presume you can see it on your side as well.
Yeah, I can see these questions. So this is Slido, right?
This is Slido. Yep, these are the Slido questions. Okay, so the first question we got is that you noted excess energy decreasing efficiency of the PV cell. What is the relationship like during colder seasons? Is the relationship positive or negative, strong, or more so linear?
Right. So it is okay. So the efficiency drops linearly with cell temperature, right? So if you have a given PV cell technology and you watch the PV cells increase what's it called in temperature, the operating temperature of the cells, the amount of electricity, the amount of, let's say, the amount of electricity you can yield, right? And which is a directly correlation of the efficiency will decrease as the temperature within the cell goes up. And that has to do with a solid state physics phenomenon of too many of the electrons not moving in the correct, let's say, the correct direction of travel, right? Now, that's a kind of a strong linear relationship. Yeah. So that's the answer to that question is yes. It's a strong linear relationship, and it's straightforward, and you can even you can model it even with like a regression model. It works out that when you look at empirical data that PV grid operators provide, and they say, well, these are the efficiencies we obtain, and this is the cell temperatures that we have. You can model it, and you get a very high R squared, showing that yeah, it's a direct negative correlation between cell efficiency and cell operating temperature.
That's very cool. Second question I've just highlighted. Did I hear correctly that the POA is a factor of potential improvement if sun-facing movement is used?
Ah, right. Okay. So um, I don't want to step into a debate, so I'm just going to take the first part of that question, which is to say that in general, if you tilt a solar panel, right, and I'm going to also see that I see that there's a third question that says on slide 29, someone has asked about the optimal tilt, at least here in Calgary, right? Um, if you tilt a solar panel, you will increase the amount of solar radiation that you get, right? Now, the reason that this becomes complicated is that if you have, let's say you have like 10 acres of land outside of Red Deer, right? And you think, well, I have 10 acres of land, so I'm just going to put solar panels on them. And then, the first year, let's say you did this in 2019, and you just had flat, like kind of solar panels that are horizontally on the ground, and they're collecting GHI. And you stop for a second and you think, well, and then you listen to me talking, and then you think, well, I've heard that if I look at these panels which are flat and I tilt them, right? And in general, you want to tilt, and when you're in the northern hemisphere, especially where we are in pretty north, you want to tilt them towards the equator because that's where you would catch most of the sunlight, and you tilt them at the optimal tilt angle, which I will get to in a minute, right? You will catch more solar radiation per panel that way. However, you would then have to make sure that the rows of panels do not overshade each other. In other words, you have to have inter-row spacing, and that means that a big chunk of your 10 acres now has to be kept empty, or a bigger chunk than was kept empty before. Right? Before, all you had to do was make sure that you could do like maintenance and operations and kind of cleaning on the panels. Now you don't really have to worry, and now you have to worry about that, and you have to make sure they're not shading each other. Incidentally, and this is a whole other segue, shading not only affects PV technology, solar PV technology, but also affects wind turbines. So if you look at wind farms, you find that they're like organized in like really crazy ways. And a big part of that is that you just don't want one turbine to harvest so much of the wind that there isn't wind energy to go to the turbine behind it. So yeah, it's a crazy world. Now, what is the optimal tilt, at least here in Calgary? How long is a piece of string? So the easiest answer to that, there's a paper by two Romanian authors called, I think they're Romanian, Stanicu and Stanicu, and they suggest that, to quote from memory, they suggest an optimal tilt, which is equivalent to the latitude. So in Calgary, I think that's like 52 degrees north, plus the solar declination angle to give you a monthly value. The solar declination angle actually, yeah, okay, that's a tough one. So that actually varies by day. But if you take the median day of each month, you can get a different value, and you can sort of plug it in, and you can say, and so in Calgary, but in general, a simpler kind of not so great approach, I think, is to just tilt all panels above 45 degrees north. So that indeed includes all of Alberta at 45 degrees from the ground facing south, right? So that's like one kind of very simple algorithm that will indeed probably give you, over the course of a year, more solar electricity than if you just have them flat on the ground to collect GHI. However, if you really wanted to look to get the optimal tilt for your solar panels and you're living in Calgary, I would probably go with something at least as complex as what Stanichu and Stanichu suggest. And there are different, there are different ones. And on my on one of my blog posts, I definitely did talk about how to work that out, but it involves a little bit more solar calculations that I can explain in a Zoom talk. So perhaps I'll wait until I send you guys the complete slides and also the code snippets.
No worries. Sounds like a topic for another blog post, but that's great. Last question that we'll take here is the website that I'm not going to read, is that the data source?
Yes, that's correct. Yeah, I'm not sure what the LARC stands for, but yeah, that's the one. It's interesting thing about that group of people. They also respond to emails really well. So they make it very easy to download all sorts of data that's like geographically specific to your house. Keep in mind, they make, I'll two caveats about NASA Power. One of them is that their satellite images, they do not make a claim to have a spatial resolution higher than 0.5 degrees. So in terms of latitude, 0.5 degrees is like 50 kilometers roughly. And in terms of longitude, that actually does vary. Because the distance between 1 degree longitude and another does vary with latitude. It's a kind of a complicated thing. I don't know how much time you guys have for that, but it's about 1 degree, if I remember correctly, 1 degree latitude is 111 kilometers, and if 1 degree longitude goes down as you go closer to the poles. So anyway, there's a kind of a spatial resolution issue there. But for almost all applications that I can think of, that's still fine. I don't know if you're talking about building a PV farm and pitching it to the bank to get a loan. I don't know what the bank would say. The second thing is that they have a huge number of parameters that you can download. One of them is something called the EF max optimal tilt, which means they predict what the maximum insulation on a PV panel at the optimal tilt for a given latitude is. I actually found out the hard way after a lot of egg on my face that that parameter is not consistently maintained for all regions of the world. And I'm pretty sure because at that time I was living in the Netherlands, and they said, yeah, no, this parameter does not work for where you are. I don't know if they fixed that, but you have to kind of, it's worth, if you're planning a kind of like a more serious project, it's worth dropping them an email before using their data. But in general, it's pretty good. Like, especially if you're at like an early stage of like planning a research project or even a PV farm.
Fantastic. Thank you. Okay, so that's thank you for answering all the questions in a great presentation, Abed. That concludes the formal part of this meetup. So thank you very much, everyone, for attending. Abed, thank you very much. That was incredibly informative, and for anyone who's enthusiastic about solar or R, that's there was a great primer to everything. So thank you very much.